Hello, Uday. Am I
Sir,
audible?
yes, sir, yes, sir. Echo ಇದೆ sir, echo ಜಾಸ್ತಿ.
Okay, closed room ಅದು, so echo ಇರಬಹುದು. I'll just put the speakers on. ಇವಾಗ? Yeah. Okay. I was just seeing whether it is recording or what. Yeah. So we shall start with the ಹೇಗಿದ್ದೀರಾ? All good? ಯಾರು? Good. Thank you. ಯಾರು ಜಾಯ್ನ್ ಆಗಿಲ್ಲಲ್ಲ? So I was just asking. Okay, so this is the seventh module, right? This is power system optimization and AI applications into power system. A very larger area where AI need to be kind of involved a lot, not at to the market. So this is a roadmap of how this session will be. Okay. Yeah. So this is the roadmap how we are going to take up this. First, we'll have a course introduction and structure, modules, timeline, and where this session fits. And then we can have an overview of the power system optimization, need for optimization, why we need to optimize it. Okay. There we are going to discuss about the economy, environmental reliability cases, technicality of optimization, objective functions. See how we formulate uh, the power system, like if you want to maximize the power, if you want to minimize the power and all, is what we're going to look at the objective functions. Then we have equality and inequality constraints. So this is a complete roadmap of how this today's class will be. See, if you want to know the course at glance, see, first you have the introduction to power system optimization. That is where you have linear programming, non-linear programming, TP and OPF and all. Then you have economic load dispatch and unit commitment. Then you have AI techniques in machine learning, DL, RL, all these things, neural networks and all. So then you've got renewable energy integration optimization, smart grid and AI application case studies and discussion. Okay, well, so these are the 10 sessions what we have planned. So here we got 10 days of class, as you can see. So today we are going to look into the fundamental functions and constraints. Tomorrow we are going to learn about the linear programming. Then we are going to learn about the non-linear power programming and all. Okay, then we are going to learn about the economic load dispatch. Mostly this one class I might be busy on that day, so I may not be able to handle on fifth session. So I'll extend that session to next maybe on Saturday. No, Saturday also I'm a bit busy, maybe Sunday. Okay, so second week again we can run with a similar functionality. uh, is this clear? Am I audible? Yeah. Yeah. So well, so what you'll learn from this from today's class, one, you will know the definition, explain, you can have it in your own word, what is an optimization problem and why power system needs one solved continuously, not just once. Then you'll have a justification of articulate the economic, technical, environmental, and reliability cases for optimization with a concrete example of each one of them. You have formulate write down the complete objective functions, including coefficients and their units for simple generation cost problems, right? And then you distinguish and apply these techniques. So if you want to start with overview of the power system, see, every decision a grid operator makes, how much each generator should produce, what voltage a substation should hold, which line should carry which flow, is underneath the engineering language the solution to a mathematical optimization problem. See, this part builds the vocabulary. So moving ahead, you can see here we can have a quick refresher because you know what is power system by already, right? You might study it in your engineering classes. So power system moves energy through four broad stages. One is generation. Second one is in generation you have thermal, you have nuclear, you have hydro, you have renewable plant convert primary energy, right? Like coal, water, uranium, sunlight, wind into electrical power. Then you got the transmission. So high voltage lines, typically 220 kilovolts and above in India, they carry this power over a long distance, right? With a very minimal losses. Third comes the distribution. So step down substations reduce voltage and fan the power to power out to local networks. And last one is the load, that is homes, industries, commercial users, finally consumes the power. So, as you can see here, uh, I have already put it, I also put it here. Every arrow here hides a uh, decision here. What decision? When it comes to generation, okay, how much should each generator produce? And when it comes to transmission, along which lines power should flow, right? At what voltages each substation should operate. So power system uh, I mean, so here what I'm trying to say is power system optimization is the discipline of answering the questions in the best possible way continuously as conditions change minute by minute. Okay, so see why this refresher matters to us. See, generation and load are physically separated by transmission and distribution, right? And there is no large scale, cheap way to store back the electrical energy. This single physical fact is the root cause of nearly every optimization problem. So, uh, that is where we are kind of having that hiccup or how to deal with this situation, because majority we cannot store energy. That's a large bulk energy cannot be stored. The batteries and all are very small devices, right? Going ahead, you can see what is optimization, the general idea here. So, in everyday language, to optimize something means to make it as good as possible. Okay. So, we have mathematical optimization is more precise. It is a process of okay. So, mathematical optimization is more precise, right? It is a process of choosing values for a set of variables. See, consider a familiar analogy, like suppose you are planning a road trip, right? And want to reach your destination using least fuel. Your variables are the route you take and your driving speed. Your objective is fuel consumed. So your constraints are the roads that actually exist, the speed limits on them, and the time you have available, right? So you are not free uh, to choose any route or any speed here. Okay, only ones that are feasible, and among the feasible choices you want the one that minimizes your fuels here, right? So these variables, uh, and objective and constraints appear in every optimization problem you will encounter in this course. Okay, no matter how complex. See, so learning to identify three pieces in the new problem. Okay, one is a real sense, the core skill. This session is trying to build. So optimization is not trying to do well. It requires a precise, quantifiable, objective and precisely defined set of allowed choices. Without both, the word optimal has no meaning here. So optimal with respect to that and among which opinions. So the three pieces, part one, decision variable. So when we talk about the decision variable, uh, these are the quantities that actually are under our control. Okay, so the things which you are free to choose. Just the example what I was giving you was a free road trip analogy. The route had speed where decision variable, and nobody hands them to use with uh, hands them to us, right? We select them. So in power system, decision variables are typically set points. that an operator or an automated control system can adjust. How much active power a generator produces, what voltage a generator is told to hold, right? Whether the transformers tap is at one position or another, where the switch is open or closed. So a useful test for whether something is a decision variable, like can can I as the operator directly set this value? If yes, it is a decision variable, right? If the value is instead a consequence of other choices, for example, the current flowing through a specific line which depends on everything else in the network, it is usually not a decision variable, but something we compute afterwards unconstrained indirectly. So part 2 is the objective function. When we talk about the objective function, is a single number we use to judge how good a particular choice of decision variable is. This converts an entire operating condition of the power system, every generator's output, every voltage, into a comparable value expressed in some unit we care about, rupees per hour, megawatts of losses, or ton of CO2 per hour. See, the reason we insist on a single number uh, rather than a list of separate concerns is that optimization needs an ambiguous way to say this choice is better than that choice. Okay, if cost went down but losses went up between the two choices, which is better, without collapsing this into one number or one carefully weighted combination as well, right? See, the question has no defined answer here. uh, so what we the objective function is very often the total fuel cost of generation, because minimizing cost is the single most common goal in day-to-day power system operations. But as well, we see in the part 4 of this session, okay, where losses, emissions, voltage deviations are equally valid objectives. So the mathematics doesn't care which one we choose, only that we choose one clearly here. So the third is the constraints. What do you mean by constraints? See, constraints are the rules that which actually bends us down, which actually ties us up, or limits which values the decision variables are allowed to take. You don't have the complete freedom. There are some constraints which they pull you back. They exist because the real world imposes limits, and also many challenges that no amount of wanting a lower cost can override. A transformer cannot carry more current than its winding insulation allows, right, without overheating. Total generation cannot differ from total demand because there is essentially no way to store the imbalance. See, why constraints matter so much? See, without constraints, minimizing generation cost has a trivial and a useless answer. Generate zero power everywhere, since has zero cost, right? It is only we require that demand be met and that equivalent limits be respected, that the problem becomes the meaningful engineering question we actually care about. That we will discuss in the fifth part of this session. Okay. Overview of power system optimization and working definition. See, the process of determining the best operating point of a power system, right? Such as generation levels, voltage settings, switching states, that minimizes a defined objective while satisfying all physical and operational constraints of the network. Best operating point, this is the outcome of solving the optimization problem. Okay, best operating point, a specific a numerical value for every decision variable, not a general strategy or a rule of thumb here. Okay, the next one is minimize or maximize the defined objective. Best only has meaning relative to a stated goal. The same power system has different best operating points for minimum cost than for minimum loss. While satisfying all constraints, the word all is doing really real work here. A solution that is cheap but violates even one equilibrium limit or power balance is not a valid answer at all. However, when it comes to the low its costs, that is one of the constraint also, right? Economically, when we look into the power system operations, when you balance the power, when you to balance the power, you have to meet the load. You have to meet the load. You have to increase the generation. To increase the generation, we have optimal generation points, or we call it as a unit commitment, optimal dispatch algorithms. When you combine all these things, uh, low cost comes to a question there. Is it possible? We can minimize the cost with all these aspects. Of course, we can meet. That is the point what we call it as an optimal point. Okay. So, why formalize this mathematically at all? See, I experienced operator. Uh, he can often make more reasonable decisions about generation dispatch just from intuition and experience. It is fair to ask, right? Then why this module is insisting to have a formal mathematical optimization rather than trusting a trained human judgment? The answer is scale and precision. See, the real interconnected grid may involve thousands of generating units, tens of thousands of buses, and decisions that must be re-evaluated every few minutes as demand and renewable output shifts. So no human, however, is experienced can mentally resolve a problem of that size that often, while guaranteeing that every equipment limit is respected simultaneously. The second reason is verifiability. See, mathematical formulation, let us prove, not just believe. It comes with a scientific proof, also mathematical proof rather, that a proposed operating point satisfies every constraints. You'll have all the constraint. I mean, you'll have all the operating points in figures, in numbers. So if one number is varied or exaggerated or bulge a bit, you can understand the constraint. What is the limit line laid here? What is the boundary? Do we have a optimal generation? Okay. So and also the mathematical formulation lets us to quantify exactly how far solution is from the true minimum cost. See, this is essential for a regulated industry where operators must be able to just dispatch decisions with auditable numbers, not intuitions. This does not make human judgment irrelevant at all. See, operators still choose objectives, interpret unusual conditions, and override automated results when something looks wrong. But the routine, repetitive core of the decision, how much should each of the thousand generators produce, right now is exactly the kind of problem mathematical optimization is built to solve reliably, quick, and at scale. So now we can see where exactly optimization appears in our power system. See, generation scheduling, we can take this each one of them, okay, and then you have economic dispatch and yeah, economic dispatch, unit commitment. See, generation scheduling is fine. See, deciding which units run and when over a planning horizon, right? But going down now, we have session 4 and session 5, where I mean the modules where you have completely you will have to deal with the economic dispatch, unit commitment. Okay, uh, since we build up, I mean then you have optimal power flow. See, economic dispatch is somewhere allocating among already running units at a least cost. When it comes to unit commitments, it's day ahead on and off decision for generators including startup cost, right? Then we have optimal power flow. See, full AC network, feasible optimal operating point, all buses, all these things comes into picture. Network reconfiguration, so choosing which switch states in the distribution network to reduce the losses. Then you have the renewable integration. This is a bit of unpredictable, but still it's an add-on. Why it is an add-on? Because uh, rather along with our conventional energy generation, we are going through an renewable energy integration. Okay, well, so when you are looking into the economic dispatch, unit commitment, and optimal power flow apart, these three problems are the workhorses of power system optimization. And so here you can confuse them because they sound similar, right? Economic dispatch, unit commitment, optimal power flow. Here is how to tell them apart, like how they are different in terms of what is fixed and what is being decided. When you look into economic dispatch, assumes fixed what? Which units are on, fixed already known, decides how much each on unit should generate to minimize cost, but to power balance and generator limits, right? When it comes to unit commitment, assumes fixed nothing here. This decides economic dispatch input. So which unit to turn on or off over the next 24 hours, including startup, shutdown costs, then the dispatches each. Now you got optimal power flow. What are the assumptions? Usually which units are on. What they decide, generation and full network voltages or flows together, enforcing every line and voltage limits, not just total balance. So this what decides them, this right side thing you can see here, this gives you a very clear picture of how each one of them are pretty different even though they sounds the same. Okay, in this part we shall go to the second part, that is a need for optimization. Okay, the economic driver. What is the need for optimization? At least by now, are you people aware of what do you mean by optimization? Hello.
Yes, sir. Yes.
This is not recording. I think if I move the screen, this is not recorded, man. Whatever I taught you till now is not recorded. No, it is recording. Okay, fine then. No problem. Okay. Can you tell me what is the need of optimization then? Hello.
Yes, sir.
What is the need of optimization? Salman. Okay. So, did you understand what? Hmm.
Improve the performance.
Performance. What do you mean by optimization? What do you mean by performance? Optimization in everyday language means, did you read that? Make it as good as possible. Mathematically, optimization is more precise. It is a process of choosing the values for set variables from among. Did you go through this? This was my second slide, man. Optimization is the thing where you have different constraints, like the generator. You know we have only 11 kV of generation from the generators. Why don't you go for 13 kV, 14 kV, 18 kV, 19 kV, 92 kV? Because 11 kV is the optimal. That means it consumes, just like in your car, even though your car goes at 180 kilometers per hour, you choose to drive your car only between 80 to 100. Why? Because that gives you good mileage. It reduces your cost, and also speed is good. You're not compromising with the speed. 100 to 80 is a very safe speed, isn't it? That is called optimized driving. Okay, Similarly, in generation, in distribution, in transmission, we have optimization. That is the need for optimization. That is what we are going to study here. See, the economic driver it is. Fuel cost dominates here. Okay, fuel cost. But can you think of the same thing in a F1 race? You can't. There, the speed is the matter, not the economy, not the fuel cost there, right? So, fuel and generation cost is in almost every utility the single largest controllable operating expense, often larger than transmission, maintenance, and staffing cost combined. Okay. See, this alone would justify careful. This alone would justify careful optimization. But the effect compounds because of the scale. You know, larger grids may burn more fuel every single hour. Consider if you have two generators supplying the same total demand, one with a low incremental cost, one with a high incremental cost. If low cost unit is underutilized by even a small amount and high cost unit compensates, the cost difference is paid every hour, every day for as long as the inefficient dispatch continues. A seemingly small 1% dispatch inefficiency sustained continuously across a large grid become a very large absolute sum over a year. This is precisely the kind of problem economic load dispatch is built to solve. Given a fixed set of running generators, a fixed demand, a fixed split up of output across generators, that maximum total fuel costs, exploiting exactly this difference in incremental cost between units. So this was, see, optimization, I'm trying to explain it in different ways. One was the economical driver. Next we'll look at the technical driver. So here we are, the main intention of this slide was to minimize the cost. Is that the optimal way of generating? Certainly not. Okay, why? Because we have something called losses and voltage stability also. If you keep on generating at very economically, you can't, means only if you are trying to save the money by in generation, no, you can't meet the optimization. So what is the next parameter which matters? The technical driver. Every ampere of current that flows through a transmission or a distribution line dissipates some energy as heat. You know that what are the losses, right? The power is, or the current is converted into heat, that is proportional to the square of the current, that is I square, we call it as I square R losses. And that current is routed, which is a direct consequence of how generation is dispatched across the network, right? Determines how much energy is lost before it ever reaches a customer. So second one is the voltage, right? That's a related concern. If your current is getting lost by means of any other parameters, or let us stick to the heat only. So every piece of equipment on the grid, from an household appliance to a large motor, is designed to operate within a narrow voltage band, right? In India, it is 210 to 220 volts, right? Voltages that drift to high stress insulation, uh, and voltages that sag too low can stall motors, and in the worst case cascade into voltage collapse across a wider area. These are the consequences. See, both losses and voltage profile depend upon the same underlying decision variable, that is generation levels, reactive power support, transformer taps. That cost based dispatch also touches here. See, this means a dispatch that is optimal purely for cost is not automatically technically sound. Loss and voltage limits must be enforced as constraints, or in more advanced formulation, they should be folded into objective itself, which is exactly the role of optimal power flow plays. Role optimal power flow plays later when we discuss the other topics. See, first one was economic driver, second one was technical driver, the third comes the environmental driver. See, different generator technologies emit very different amount of pollutants. It might be sulfur oxide, nitrogen oxide, sulfur dioxide, nitrogen oxide, greenhouse gases like CO2 per unit of energy produced. A coal-fired unit and a gas-fired unit meeting the same demands can have emission profile that differs by a larger factor, even if their costs are comparable, right? Increasingly, regulatory framework and corporate commitments requires utilities to report and limit emissions, not merely minimize cost here. Okay, this turns emission into either a hard constraint, an emission cap that must not be exceeded, or a second objective to be traded off against cost, which is exactly the multiple objective formulation we are going to study in the part 4 in the same in today's session. Okay, so the practical consequence is that, okay, if I have to put it in one single word, what kind of generation, what amount of generation will lead to very less amount of uh, pollution. Okay, that comes in the economical driver. Then comes the reliability driver, security under contingency. This reliability driver is, see, you are for you are concentrated on last three, that is economical driver, that is technical driver, and the environmental driver. And you have set a point where you are generating the power now. If the load goes up, is your economical constraint is in a position to compensate the exceeded load? That's what comes into picture. That is where the reliability comes into picture. It's so not only when the load goes up. If one of your supplier fails to supply energy, like renewable energy, it's a rainy season, you are not getting the power from the sun, what are you going to do now? These are the points where reliability driver comes into picture. So a power system must remain stable not only under normal conditions but also immediately after the sudden loss of any single major piece of equipment, like a generator tripping offline or a transmission line being disconnected by a fault. This requirement is usually called N1 security. The system must survive the loss of any one of its N major components without cascading into wider failures. So meeting this requirement means system must always be carrying a spare capacity, reserve generation that is not currently needed to meet demand but is available to be brought online within seconds to minutes if a contingency occurs. Okay, how much reserve to carry and where in the network to locate it? See, is itself a optimization problem. Too little reserve risks instability, too much reserves waste capacity and money. Okay, optimization formalizes this trade-off, seizing reserves against the actual probability and consequence of contingencies rather than a fixed conservative rule of thumb. And it does so systematically enough that the resulting dispatch plan can be verified in advance to survive every credible single contingency scenario, not just the ones an operator happens to think of. So what is the need for optimization? Again, this is the scale of problem in numbers. You can see thousands of generating units coordinate on a single interconnected grid. Less than 5 minute typical redispatch cycle for economic load dispatch in real time. 1% dispatch inefficiency can translate into massive avoidable fuel cost annually. So, concrete illustration here is, suppose a grid serves an average load of 10 megawatt and average generational cost is roughly 4 per kilowatt hour. Total spend on energy alone is approximately, how much is this? 100 lakh, that is 1 crore kilowatt into 4 rupees per kilowatt hour, that is 400 lakhs, that is 4 crore per hour. Even a modest 1% reduction in average cost achieved purely through the better dispatch, not through the burning less fuel overall, this simply through a smarter allocation amongst its units, saves roughly around 4 lakh every hour or well over 300 crore annually. This is the entire economic case for economic load dispatch is in one calculation. Now at least you understood why optimization is required. And here you have a table without and with optimization, and why. See, without optimization, higher fuel costs and operating costs, unpredictable voltage profile, larger unplanned reserve margins, slow manual contingency responses. Let's have a look. Why is this happening? Right? So, higher fuel and operating costs, because without optimization you keep on switching on the generator and switching off the generator very realistically, so it keeps on producing it keeps on increasing your cost. Unpredictable voltage profiles, of course, without having a proper reactive support, uh, transformer taps, all these things. So network, your network may behave very unpredictably, right? And last one is the large and unplanned reserve margins. So without having a quantified risk trade off, you have to, unplanned reserves need to be made large. You need to have that unplanned reserves, right? Slow manual contingency responses, no pre-verified plan exists for each credible failure there. So with optimization, what happens? Least cost generation schedule, because you have a proper generation schedule. If this generator fuel is going down, or you're not getting enough supply from any other part of the grid, very quickly you will transfer, or else enhance the scale of your generation on the other side, so the load is properly maintained, right? So output tracks each unit's true incremental cost automatically. Then voltages held within secure limits there, reactive support and taps solved jointly with real power, reserves size to actual system needed, fast systematic contingency responses. A brief historical perspective, heuristic experience based on economic dispatch, guided by engineer judgments and simple tables, and Carpenter formalized the optimal power flow problems as a rigorous mathematical program in 1962, right? When it comes to 1970s and to 1990s, linear programming, nonlinear programming solvers mature digital energy management system and become standard in control system. 2010 onwards to now, it is all about AIM and ML argument, classic optimization, handling scale, uncertainty, and speed beyond classical solvers alone, right? So this is how our approach towards the optimal dispatch, power system optimization has changed for last 100 years. 1920, now we have to 2026. So this is how uh, optimization has evolved. Okay, now after getting to know about the need of the optimization, we shall move along for the structure of the optimization problem. Well, when it comes to anatomy of optimization problem, you have decision variables, right? Yeah. So here, every optimization problem, however they are complex, they are built for an exactly four pieces: design variables, decision variables. It is denoted by x in this case. Then you got objective function, that is denoted by fx here, and a set of equality constraints denoted by g of x, and set of inequality constraints denoted by h of x. Together they combine into the following template here, right, which we would memorize as uh, f of x subject to g of x, equality and h of x lesser than or equal to 0, that is inequality, right? So now do one thing, you read from left to right. We search overall decision variables, right? For the one makes f of x smallest, but we are only allowed to consider x that makes g of x exactly 0 and keep h of x or at or below 0. Every optimization problem in this course is a specific instance of this exact template. So what changes from problem to problem is the only what x, f, g and h stands for physically. So decision variables, what I was talking about x here, we shall have a look into them. So we know now make the abstract symbol x from the previous slide, right? In power system, x is almost always built from combination of the following physical quantities. That is PGI, you already know this, reactive power output of the generator I measured in megawatts. This is the quantity that actually does useful work, turns motors, lights, bulbs, electricity, and is almost always the primary decision variable in the dispatch problem. Then we have QGI, that is reactive power output of the generator I measured in MVAR. This does not do useful work directly but supports voltage across the network. Generators can typically produce it somewhat independent of PGI within the coupled limit here. So then you have VI, voltage magnitude at bus I. So in power unit of nominal rated voltage, we call it as in PUs. The value of 1 PU means the bus is exactly at its rated voltage until typically that requires VI to stay within roughly 0.95 to 1.05 per units. Then we have discrete variable. You can see here a discrete variable. When you look into the discrete choices, not every decision variable is smoothly adjustable number. Some are discrete. They take only one small fixed set of values, and this distinction matters enormously for which solution method applies. See, transformer tap changer position for transformer K, and integer step example -8 to +8 that adjust the voltage ratio in discrete increment, not continuously. Then you have UI, on off commitment, status of generator unit I restricted to 0 and 1. This single binary variable is what makes unit commitment fundamentally harder to solve than economical dispatch. Then you have SK, that is switching state of linear or breaker K, also in zeros and 1, open and close. Okay, the decision variable behind the network reconfiguration problems. Fine. Next we shall go to the objective core, that is objective functions. Let's have a closer look. What is an objective function? See, formally, objective function is a mathematical expression written.
ಸರ್ ವಾಯ್ಸ್ ನೀಟಾಗಿ ಬರ್ತಿಲ್ಲ ಸರ್.
Hello.
ಹಾಂ ಸರ್ ಇವಾಗ ಕ್ಲಾಸ್ ಇದೆ.
ಏನಾಯ್ತು?
ಅದು ವಾಯ್ಸ್ ಸ್ವಲ್ಪ ದೂರ ಹೋದಂಗೆ ಥರ ಕೇಳಿಸ್ತೈತೆ ಸರ್.
Okay, okay. Uh, Fine. So formally, see, when we talk about an objective function, that is a mathematical expression, right? Written in terms of decision variable, whose numerical values we want to minimize or maximize. We write it this generally as a function of x1, x2 to xn, where x1 through xn are the decision variables. And when you look into the the function denotation f is a rule for combining them into one number. So two properties of good objective functions are sorry, uh, worth uh, internalizing early. First, it must be computable from the decision variable alone, and if evaluating it required information we do not have, like tomorrow's weather, right? It could not guide us to today's decision. So, second, it must genuinely reflect what we care about. A poorly chosen objective can lead to a mathematically optimal, okay, answer. Optimal answer that is practically useless. For example, an objective that ignores emission entirely will happily recommend the dirtiest available generator if it happens to be cheapest, right? In power system, FX is almost always expressed in engineering units that a manager or a regulator would recognize immediately, right? Rupees per hour for costs, megawatts for losses, tons of CO2 per hour for emission. So this deliberates, it keeps mathematical traceable back to something physically and financially meaningful. So, common objective again, cost minimization, loss minimization, emission voltage deviation. These are the few things what we looked into in the previous topic also, in previous part also, right? There we studied it as economic constraint, from the economic perspective, from the environmental perspective, right? Very similarly, here also we are going to have a look the common objectives. See, when it comes to cost minimization, this is a difficult objective in day-to-day power system operations. See, for its objective is most directly tied to an utility's financial performance. It is the easiest to measure, unambiguous that every fuel purchase has a rupee value. And as we all see in part, anyways, we are going to look into the part 5. Okay. The resulting mathematical problem tends to be well behaved, convex, which makes it reliably solvable. So, cost being minimized is typically the fuel cost of thermal generation expressed per generator as a function of the generator power's output. So we will derive the standard mathematical form for this, the quadratic fuel cost curve, over the next several slides, right? Since it is the single most important formula in this entire session for us today. Second one is the loss minimization. This is completely technical, right? Instead of cost, a utility may choose to minimize the total transmission and distribution losses. In turn, they will feed you to the cost optimization or cost improvement minimization. Actually, if losses are less, the required generation will be less. So if the required generation will be less, of course the fuel cost or operational cost or many things will reduce there. So loss minimization is also very much important. Rather than there is a very beautiful word with the Bescom people, I guess. It is every unit of energy saved is equal to every unit of energy produced. So it's the same funda. Okay. So a utility may choose to minimize total transmission and distribution losses. The energy that is generated but never reaches a paying consumer customer dissipated as heat in the conductor along the way. This is a major loss we have to think of, right? Other than that, we have reactive power losses and many other things which all contribute to the point where uh, heat dissipation is also accountable. Okay, so loss minimization typically leads to a different generation pattern than cost minimization. It tends to favor generators located electrically close to the load, even if their even if their fuel cost is somewhat higher, because shorter electrical distance uh, means less current squared along the path, that is direct squared along the path. This is a clear illustration of why the choice of objective genuinely changes the answer, not just its framing. See, in practice, loss minimization is most often used as a secondary objective or as a constraint. Keep losses below X%. Like, even though you cannot mitigate the losses completely, keep it below X%, layered on top of primarily cost driven dispatch, rather than as the solo objective. Pure loss minimization taken to its extreme uh, could recommend an expensive but electrically nearby generator over a cheap but distant one. Common objective 3 and 4 combined together emission and voltage deviations. So, Uday, hello, Uday.
Yes, sir.
What is the duration of the class?
Sir, actually 3 hours sir.
Hmm.
9,
Hmm.
6 to 9 ಇದೆ ಸರ್ 3
Hmm.
hours ಮಾಡಬೇಕು.
Okay.
ಹಾಂ ಸರ್.
ಬೇರೆ ಸಬ್ಜೆಕ್ಟ್ಸ್ ಎಲ್ಲ ಹಾಗೆ ಫಾಲೋ ಆಗ್ತಿತ್ತಾ 6 to 9?
ಇಲ್ಲ ಸರ್, ಅಂದರೆ ಪ್ರಿವಿಯಸ್ ಮಾಡಲ್ ಅಷ್ಟೊಂದು ಏನಾಗಿಲ್ಲ ಸರ್.
ಎಷ್ಟಾಗ್ತಿತ್ತಪ್ಪ?
ಮತ್ತು ಅನಿಲ್ ಸರ್ದು ಫುಲ್ 3 ಅವರ್ಸ್ ಮಾಡಿದ್ದಾರೆ ಸರ್, ಅನಿಲ್ ಕುಮಾರ್ ಸರ್.
ಓಕೆ
ಎಕ್ಸಾಕ್ಟ್ 3 ಅವರ್ಸ್.
ಓಕೆ. ಬೇರೆಯವರು?
ಆಲ್ಮೋಸ್ಟ್ ರೀಚ್ ಆಗಿದೆ ಸರ್, 2
ಓಕೆ 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 ಫೈನ್. So, when it comes to emission and minimization, it treats the pollutants or greenhouse as output as the quantity to minimize using an emission curve, right? For each generator analogous in form of, sorry. Sorry. So, it costs the curve typically also expressed expressed as a polynomial in that generator's power output, but with the emission rate coefficient instead of cost coefficient. Okay. So, voltage deviation minimization is different in character. Rather than minimizing cost like quantity that grows without bound, it minimizes how far every bus voltage sits nominal voltage sits from its nominal value of 1 point, 1 per unit, typically expressed as a sum of squared deviation, that is summation of Vi minus 1 whole square, right? This objective is used when voltage quality itself, not cost or loss, is the primary operational concern, such as during planning of network with many voltage sensitive industrial loads. So, when we are talking of all these things, uh, consider all the four objectives introduced so far. One is the cost, the other one is the loss, emission, voltage deviation. Share the same mathematical skeleton, some functions of the decision variable to be minimized. This is exactly the generality where highlighted on anatomy slide, okay? And it is why every technique we learn to minimize the cost will apply essentially unchanged to any of these other objectives. So the next one is fuel cost function, where the formula comes from. The thermal generator's cost of producing power is not proportional to its output. It costs more per additional megawatt to push a plant towards its maximum output than to run it at a comfortable mid-range level. This behavior is captured with a quadratic, that is second degree polynomial function of power output. So you can see here there Fi, Pgi, like Ai, you have the formula there. Ai is the quadratic coefficient, curvature of the curve. Bi is the linear coefficient, incremental cost nears to 0 there. And then you got Ci, no load cost, fixed or no load cost, even at Pgi is equal to 0. So the Ci term represents cost incurred simply by keeping the units running and synchronized auxiliary power. So minimum fuel to sustain combustion regardless of output. The PGI term is the dominant, roughly linear cost of fuel burned in proportion to output. So the AI PGI square term captures the fact that heat rate, fuel burned per megawatt hour produced, worsens as unit is pushed towards its upper limit. So cost rises faster than the output near maximum capacity. Okay. So why quadratic specifically? See, a quadratic is the simplest polynomial that can bend upward, convex, okay, matching the physical worsening of the heat rate at high output. These are all, kind of quick read things. Why I'm trying to give you is it will give you a more clear understanding. So when we try to read the cost curve, And marginal cost, you can see here the values have been given 0.004 pgi square, okay, for 5.3 pgi. Now you compare the same thing with this formula. So ai, that is quadratic coefficient curvature of the curve, is 0.004. That is what is indicating you the ai. 5.3 is your bi, right? Similarly 500 is your CI. Okay. So when it comes to convexity, what it means and why it matters. See, the function is convex if a straight line joining any two points on its graph never dips below the curve. So visually the curve is bowl shaped, curving upwards. So our cost curve satisfies this because AI is greater than 0, right? Marginal incremental cost, the slope, what you can see here, right? At any point, its derivative dfi by dpgi is equal to 2ai pgi plus bi is the cost of producing one more megawatt at that operating point, because the curve is convex, right? The slope is always increasing. The more a unit is already producing, the more expensive its next megawatt becomes. So this is a small worked example evaluating the cost functions. As you can see, F200, the same form, we are using the same formula. So PGI is equal to 200 there. So F200, you have a question here, a generator cost functions FPG is equal to something rupees per hour. Find the cost of operating it at PG is equal to 200 megawatt and identify each term's contribution. So when you substitute this formula, we substitute PG directly into the formula. This is simple evaluating the function at a specific operating point, exactly as we could evaluate any function at a given input. So the quadratic term, that is 200 square is equal to just give me a second. Hello, sir. ಹಾಕೋದಿರುತ್ತೆ ಹೆಸರು ಬರೆದು ಕಳಿಸ್ತೀವಿ, ಅವ್ರ ಹೆಸರು ಪ್ರಿಂಟ್ ಮಾಡೋಕ್ಕೆ ಪ್ರತಿಯೊಂದಕ್ಕೂ ಏನೋ ಮಾಡ್ತೀನಿ ತಾಳಿ, ನಾನು ಕಳಿಸ್ಕೊಡ್ತೀನಿ ಇವತ್ತು ರಾತ್ರಿ. ಅಲ್ಲ, ಇವತ್ತು ರಾತ್ರಿ ಕಳಿಸ್ಕೊಡ್ತೀನಿ, ನಾಳೆ ಪ್ರಿಂಟ್ ಮಾಡ್ಬಿಡ್ತೀನಿ, ಆಯಿತಾ? Sorry, am I audible?
Yes, sir. Yes.
Yeah. So, uh, yeah. So we have just substituted the formula here. Excuse me. Yeah, I'm sorry, caught up with something. Okay. So, so directly when you substitute Pg is equal to 200 in the formula, okay. So you are getting this values of once see first you can substitute this. So 200 square is 40,000, right? So when you substitute this, you get 160. That is 160 rupees, 160 per hour, because this parameter zero point 0.4 PGI square. No, no, not zero point 0.4. That's not the formula. Formula is here. AI PGI square. Okay, so that is giving you uh, the cost of driven by pushing the unit towards higher output, as discussed in our previous slide there, right? So next point is 5.3 into 200 is 1060. This the linear term contributes 1060, okay, per hour. This is by far the largest contributor here, reflecting the roughly proportional fuel cost of running at 200 megawatt. And the last one, finally we add up all these costs, okay? So 160 plus 1060 plus 500, which will give you the total cost of 1720 per hour, right? So fixed is 29%, linear is 62%, quadratic is 9%, okay? So this is the fixed 29%, this is the linear increase, that is 62%, quadratic is 9% of the total, okay? So this is how you can understand, I mean, so when you look into this result, we can interpret here. See, getting the number of 1,720 rupees per hour is only half the exercise. So a good engineer also sanity checks the interprets. Notice from the breakdown on the on this slide here, that linear term 1060 dominates the total, contributing dominates the total, right, contributing 62% of the total cost there, while quadratic term contributes only 9%. This tells us that at 200 megawatt, at 200 megawatt, the generator is operating well within the comfortable range. The cost accelerating effect of the quadratic term has not yet become significant there. See, which can also compute the marginal cost at this point using the derivative formula from this slide here, df. You can see here anything in the quadratic curve here, I guess I showed you the formula there. Yeah, here you can have a look into this formula. This formula here, okay. Yeah, now when you uh, try to compute the marginal cost by using the derivative formula, you can see df by dpg is equal to, you don't have the plus c term here, that is missing, right? Because once we derive, this constant will go off, okay? So you'll be left out with only 2 into 0.04 times 200 plus 5.3, right? So that gives you 690 rupees per megawatt. This tells us that producing one additional megawatt, just one additional megawatt starting from 200 megawatt, would cost approximately 6 rupees 90 6.90 rupees per hour. Compare this to average cost of megawatt, that is, you can see here 1720 is your total cost, right, for 200 megawatt of power. So when you compute this, yeah, approximately this costs you 8 rupees 60 paise. So now you have marginal cost of 6 rupees 90 paise for every next, for 200 first megawatt. Your cost will be whatever for 200, along with that you will have this 690 paise because of the next 1 megawatt. So this is noticeably lower than the average cost of 8.60 at this point, isn't it? See, this gap between the average cost and the marginal cost is being lower here, and is a direct and numerical consequence of the fixed cost. Why this is happening? Because you don't have the CI, right? So this PI is spread over more megawatt as the output rise. See, recognizing the difference between the average and the marginal cost is essential. Once we reach the economical dispatch in fourth day, maybe on Thursday's class, we will be discussing that. Okay, where it is marginal cost, not average cost, that determines the optimal split up of output between the generators. See, from one generator to the whole system, now we are trying to expand the same formula for the set of generators. Here it was only one generator, right? So, the real power system has many generators, right? They will be running at simultaneously. This is where the concept of unit commitments comes into picture. So we need one objective function that represents the cost of the entire system's operations, right? Not just one units. Okay. So what is the key idea here is each generator fuel is burned and paid independently. Like generator one cost does not depends on generator two is on what generator two is doing. This independency is what allows us to build the system's wide objective by simple addition. Okay, so minimize f, that is summation of fi pgi for I is equal to 1 to n. So you have this so on up to these things. Okay, so each generator contributes its own quadratic cost terms, right? Exactly as exactly as derived earlier. So the system objective is simple, the arithmetic sum of n individual like f1, f2, you might have f3, you might have f4, go on up to fn. So N is the number of generators, right? Generating units currently committed, turned on and available to serve the load. A quantity that unit commitment, again we are going to send it in, not in this week's class, might be in the next week's, no, this week Friday I can't take, yeah, in the next week's class. So one level up from this problem. Okay, so this exact, that is called as unit commitment, we will deal with that. Okay, see this exact sum minimize subject to the constraint we are going to build there is the complete mathematical statement of economic load dispatch. Okay, so the first problem you will fully solve by hand and by method in our section 4. Someone wants to join, I think, right? No one? Okay. Well, so beyond a single goal, multiple objective formulations, that is real utilities, rarely optimized for cost alone. Okay, so the standard techniques of handling two competing goals, say cost and emission, at once is weighted sum method. Multiply each objective by a weight reflecting its relative priority and add them into one combined objective. So, we are not dealing with only one objective of just minimizing the cost, minimizing the emission, minimizing the technical like voltage stability or losses. Uh, we will try to have multiple at once. So, what shall we do? We have uh, cost PG, emission PG, but we have something called W1 and W2. These are the weight reflecting. So you got W1, W2 variable, like they are constants being used here. Okay. So weighting factors chosen by the utility or the regulator, reflecting the relative. Yeah. So relative priorities. It is common though not required to normalize, right? So what W1 and W2 is equal to 1. So what is the trade-off in this entire concept? See, lower cost often means higher emissions, okay, and that is vice versa. I'm sorry, because the cheapest available unit is not always the cleanest one. Okay, this is rarely a single choice that is based on both counts and simultaneously. Hello, hello, okay, hello.
Hello, sir.
Sir, audible ಇದಲ್ಲ ಸ್ಲೈಡ್ಸ್ ಸ್ಲೈಡ್ಸ್ ಎಲ್ಲ ಕಾಣಿಸ್ತಿದಲ್ಲ ಸರ್?
ಕಾಣಿಸ್ತಿದೆ.
Okay, okay. Thank you. I'll continue. Well, See, cheapest available unit is not always the cleanest one. The thing is, the more we go for a cheapest, maybe the quality of our raw materials or the fuel, many other many other constraints, many other hurdles do come into picture. See, this is rarely a single choice that is the best on both counts simultaneously. Okay, so Pareto front in the sense, as you can see, as we vary W1 and W2 from 0 to 1 and is resolved each time, we trace out a set of all non-dominated trade-off solution points. Okay, that will improve the objective in only, I mean, only possibly by worsening the other weighted objects, might be of the emission or of the cost. So utility will select only one of these points on this front and its operating policies. So now if you have to look into equality and inequality constraints, uh, just a quick recall of all the four parts what we try to understand now. See, now here we studied about the four objectives, right? So not four objective functions. Okay, what is f of x, and we had a formula also, right? So going behind, we had structure, anatomy. So you will be having a variable, objective function f of x. Then you have the different constraints there. So after dealing with all these things, what is the optimal solution, right? This was a structure. Before that, we had a need for optimization. You studied in four different parts, right? That is, one was economy, another was technical, the other was environmental. Then you got the reliability driver, that is, how much dependency we can have. The first one is the very beginning of this topic. So do you have any doubts regarding them? Hello. This is the very basics of your power system. I wish these are very much clear because you might have studied them. If not in depth, you might have studied them in your engineering classes, right?
Okay, sir. Yes, sir.
Yeah. So the next part is the equality constraint. I'm sorry. Uh, yeah. Equality and inequality constraints. When you look into the equality and inequality constraints, again, why constraints matter? Constraints means what? It's a limitation on which your generation can operate, on which the entire boundary is specified. We spoke about this in the very first part, but here we can have a bit of calculation, bit of equational support, and we can prove that how exactly this is happening. Okay, I'll just take this pen. Okay, you can see here uh, total cost objective we just derived there. This is what we have, right? If PGI is very, if PGI were completely unrestricted, the minimizing choice is trivial and useless, right? To set every PGI to zero or zero output costs, fixed cost CI at most actual, right? If we also allow the unit to be off, it costs nothing at all. Fine. So what is the solution is mathematically correct but physically meaningless because it ignores the entire reason we are dispatching generators in the first place to serve the demands. Okay. What exactly this statement means is if everything is equal to zero, your generation itself is you don't have a generation. Okay, and all the unit to be off. Okay, then that is the most uh, so beautiful solution to have a proper zero, I mean, cost there. But does it physically, I mean, physically it is completely meaningless there, right? You have a beautiful bike and you don't drive, you just parked in your garage, what is the use, right? So what is the first reason we are dispatching a generator is to serve the demand. So constraints are what converts an abstract minimization exercise into an specific engineering question we actually care about. So, a solution to an optimization problem is called feasible if it satisfies every constraint simultaneously. Only feasible solutions are candidates for the optimal solutions. Uh, an infeasible point, however low its objective value, is simply not a valid answer. This is why in practice engineers often spend as much or more effort correctly specifying the constraints as they do choosing the objectives. So these constraints, what is the other word we can use for constraints? That is limits. These limits on what your entire power system can operate is very much important than the choosing your objective. Okay, so these limits should be specified very precisely so that you have, I mean, it will be easy for you to deal with the other things. Well, looking into the equality and inequality, the conceptual distinctions these are, okay, not all constraints behave the same way, and the difference is not just notational. You can see is equal to versus less than or equal to, it reflects two genuinely different kinds of real world rules, right? Similarly, equality constraints, they must satisfy exactly this. These encodes physical law like conservation principles that admit no violation in either direction. Power balance is the canonical example. Generation cannot be slightly more or less than the demand plus losses. So the grid enforces this automatically whether we plan for it or not. Then we have something called inequality. So when you look into the inequality, these encoders operations are equipment lists. Their boundaries are set by design, policy, or safety margins, which a variable may approach but not cross. A generator's maximum megawatt rating is hard equipment limit, a regulatory voltage bands, or a policy set limits. Okay, so an equality constraint restricts a variable, or more generally, an expression involving several variables. Okay, now we are talking about equality constraints and how we define it. To hold exactly one value, no more, no less. That is where the equality constraint is all about, right? In general form, we write it as g of x is equal to 0, where g is some function of the decision variable x, and constraints requires that function to evaluate exactly 0. Writing the constraint as g of x rather than g of x is equal to 0 rather than g of x is equal to some target value is a notational convention, not a loss of generality. See, any equality constraints of the form expression is equal to target can always be rewritten as expression minus target is equal to 0. See, this convention will make it easier to recognize the standard problem template consistently across every optimization problem in this module. Moving ahead, so deriving the power balance equation. So you got three steps here. Okay, so here you can see the direct consequences of conservation of energy is applied to an electric network with essentially no large scale bulk storages. So start from conservation of energy. In any closed system, energy must equal energy in, right, that is input energy must equal the output energy plus energy stored. Okay, since bulk electrical energy storage is negligible on a grid, at every instant every generated energy generated must equal energy consumed with one adjustment made, right? That is account for losses along the way also. So write it single expression equal to 0 there. So this is the energy generated summation of different energy generation means different units. So here this is the total energy demand we have, this is the loss we have. When we have all these things summation, we should get it as 0. Okay, so this is the power balance equation. So when we look into the power balance equation, just like in the previous scenario, see the system demand is 500 megawatt, total transmission loss is 15 megawatt. Okay, so find the total energy required to meet the power balance constraint and explain what the answer means physically. That's the question here. So this is the power balance equation we just saw in the previous slide. So if you send these parameters across, you get this equation, PD plus PL. So here you have 500, that is system demand. Total transmission loss you have 15, right? So summation of these two, this is a kids play. Anybody can do this. It's not a big problem altogether. So this is 515 megawatt. Okay, so similarly you have a worked example. This is two, this is continue, right? Yeah, this is not, this isn't the whole story here. See, in the previous example we treated loss as 15 megawatt as a known given number. In the real power system, this simplification worth flagging clearly. The transmission losses are not a fixed constant. They depend on how current flows through the network, how much load demands the current, and we have very unpredictable load characteristics where load may increase all of a sudden or decrease. So if load increases, the rate of flow of current, or the current rating will increase, current rating increase, losses will increase, right? Which in turn depends on exactly low how the 515 megawatt of generation is distributed among individual generators and routed along specific lines, right? So this creates a subtle, subtlety, to know the losses precisely. We would need to already know the generation dispatch, but to solve for the dispatch, the power balance constraints need to know the losses. So in practice, this circular dependency is resolved iteratively. An initial loss estimate is used to solve for a first dispatch. The resulting flows are used to recompute more accurate loss figures, and process repeats until it converges. For the purpose of this session and of the economic load dispatch in section 4, say we will treat PL as either 0, okay, uh, or as a known constant. Okay, so the full iterative treatment of losses computed from actual network topology is precisely what optimal power flow, uh, what I try to describe in the part 1, is built to handle rigorously. So when we look into the inequality, the formal definition of it is, see, inequality constraints are variable that lie within the acceptable range rather than pinning to one exact value, that is a constant, what you just see in the previous example as 15 megawatt or 0, right? They were pointing towards an exact value there. They don't have an exact value, but they will be in a variable limit. Okay, so we write this as h of x less than 0, right, or less than or equal to 0. Uh, well, so h of x greater than x minimum, that is the minimum value of x, combined within the h of x lesser than or equal to h maximum. Okay, so which is more which is the more common way of writing it, or simply variable bound. So the simple most important distinguishing feature of inequality constraint compared to an equality compared inequality constraint compared to equality constraint is, here you can see that the variable sit anywhere strictly inside its bound area here, right? There is a limit, uh, but there is no requirement to sit at any particular value like 0 or 15 megawatt. No, here it is having a range or a boundary to sit in between, let alone at the boundary. The constraint is only violated if the variable tries to go beyond the boundary. So this has a direct practical consequence. We'll return in the part 5 later slides. Okay, so at optimal solution to well-posed problem, some inequality constraints will be binding. So the variable sits exactly at its limit while other will be slack, right? The variable has room to spare. So recognizing which central to understanding any optimal dispatch looks the way it does here. So when you look into the inequality constraints in practice, generators and voltage limits, you can see here generator limit. Uh, this is the minimum power to be real power to be generated. This is the maximum real power to be generated. This is the actual PG, the generation. This sits within the minimum value and the maximum value. When you look into the voltage limits, the minimal voltage, that's what we say. What is the rated voltage of India? It is 232 to 210 to 230 volts. Okay. So this VI minimum might be like 210 volts, right? Lesser than or equal to 220, what we optimally put it on the books, which is lesser than or equal to, this is the maximum limit, 230. So this is for the voltage constraint. Okay. Unequal constraints in line flow and ramp rate limits. Line flow, see, a transmission and distribution line carries currents, right? So which generates heat through the line's own resistance beyond the rated thermal limit, right? So a conductor can sag, risking the clearance violation or suffer permanent damage. This is hard physical ceiling on how much power and single line can carry regardless of what the uh, uh, rest of the network needs. So this is the thermal limit, okay, and then you have a ramp rate limit. So the thermal generators cannot change output instantaneously because it consists of boilers, turbines, right, and mechanical inertia. They have mechanical and thermal inertia. So the ramp rate limit caps how much unit output can change between one time period and the next time period, which matters directly for unit commitment. Uh, that's a later chapter. Okay. So when you assemble the complete mathematical form, okay, we have now every ingredients needed to write a complete economic load dispatch problem, right? The exact formulation again will come back to you on in session 4, how to solve. So objective 4, minimize F total cost summed over every committed generator. Equality, this is the equality. Inequality, you must be in the limits, right? So now we have a complete problem formulation. They were like very small problem. Here I am trying to give a complete problem formulation. Okay. So you got two generators serves as the demand uh, PD, right? Power 30 megawatt. You can neglect the losses here. So FG, this is a formula given, right? And then you have a limits here. Then again you have the second function array problem, and you got the limits here, same limits I guess. Yeah. Formulate the complete optimization problem. Objective, equality constraints, inequality constraints, right? Using exactly the template assembled to the problem slide. See, minimize, step-by-step solution. This is minimize F. Minimize is F is equal to Fg1 plus Fg2. So if you put Fg1 and Fg2 there, subject to equality Pg1 plus Pg2 is equal to 300 megawatt is equal to 0, right? That comes from the formula. Where is the formula actually? I think here, this formula. No, we don't have any loss here. Yeah, Pg1, Pg2. Anyways, so inequality, we have formula for it, and you got limits, right? This is the inequality. So equality, we have this formula. So power balance PD is equal to 300 here, because you can see from the formula you got PD here, right? Power demand, and also it has been said in this thing. Losses neglected, generator 1's operating range, this is a generator 2 operating range, right? So now, see, with n is equal to 2, n is equal to means you got two generators and every symbol replaced with a numerical value for a specific function, right? Formulation is mechanical ones, the template is internalized. So solving it, finding actual PG1 and PG2 that minimize cost is a job of lambda iteration method, right? uh, Yet you have not studied lambda iteration, it will be considered in our session 4. So we can give a geometric meaning to the algebra of the worked example 3 now. Every constraint carves away a part of space of possible pg1. Here you have pg1 minimum, you have pg1 maximum, right? What remains the feasible region is where the valid solution can live with the optimum, is the best point inside. It is in the sense of lowest cost. So the rectangle, what you can see is the intersection of generator limits, uh, inequalities from worked example 3 here, right? The power balance, your pg1 plus pg2 is equal to 300. The further restricts the feasible point to a line crossing the rectangle, right? So the optimum sits where the lowest cost point on that line falls, feasible region. So local optimum versus global optimum. Why convexity saves us? See, the best point within the nearby neighborhood of the feasible region within the feasible region, but not necessarily the best point overall. So a search that only compares each point to its immediate neighbors can stop here and never realize a better solution exists elsewhere. So the single best point across the entire feasible region, this is what we ultimately want any optimization method to return, and its existence in general say nothing about how easy it is to find that. So convexity guarantee, why this matters here? See, a feasible region is convex if the straight line, line segment joining any two feasible points stays entirely within the region, or rectangle intersected within a line feasible region from the previous slides, as exactly this property is, right? So this was the, this is precisely why classical methods like lambda iteration can solve economic dispatch reliable and quickly. This geometrical will never give you a precise answer, right? This is also precise why unit commitment, that will come in section 5 of a full AC optimal power flow are harder. Okay. So before we recap, tying the parts 4 and 5 together, see, step back and notice what we have actually built across the last two parts of this session. Part 4 gave us why to measure how good any single operating point is. Objective function. Part 5 gave us way to describe which operating points are even allowed, the constraints, the range, right? Together, these are not two separate topics, they are two halves of a single complete mathematical statement of economic load dispatch, assembled piece by piece, assembling the complete mathematical form slide, right? So every session of the rest of this course, okay, either teaches you a method to solve this exact kind of problem more efficiently or greater scale, or extends the problem itself, adding discrete decision, unit commitment, full network physics, that is optimal power flow, or entirely new solution philosophies. Okay, AI based methods, none of it replaces what you have learned today, all of it builds directly on top of it. Okay, so moving ahead, so you got optimization three parts. One is decision variable, the second one is objective function, and the constraints, right? We have studied about all these three things now. So in discretion variable, what we choose, in discretion, in objective function, what we measure, in third, what limits us, right? And then you have power system optimization finds the best operating point, that is subject to physical law, equality constraints, or equipment policy limits, inequality constraints for clearly stated objective. The need is economic and technical, environmental and reliability driven, and the scale of real grid makes manual intuition based operational impossible. So these are the few things what we have studied today, right? We have studied about the objective function, we have studied about the equality constraint, power balance equation, convexity of both. We tried with a geometrical approach today, which didn't work out very well, but we should go with the lambda iterations, right? So the practice questions always you can work is all these things, okay? So what I'll do, session 2 in tomorrow's class, we have to learn about the mathematical formation of linear programming problems, graphical solution methods, simplex methods, step by step applying LP to power system problems. Okay, so these are the things we need to study tomorrow. Do you have any questions?